plays outside sports in this class? Wind affects you. Baseball, like it makes a difference, right? So what if you're walking along the same path, or running, whatever, and there's wind? Sometimes it can help you if the wind is going the same direction you are. And it also matters how strong that wind is. So the last few days, it's been really strong. Today, it's not so bad, I think. I haven't been outside, but I don't think it's that bad. But if it's going against you, it's going to hurt you, right? It's going to resist. So wind either can give you resistance or help you. That's what it's going to do. How we measure something like wind is what we call a vector field. And I think you've had it before. I don't know if you had it before I came here, but for every position on the curve that you are on, X and Y, there's going to be a wind. The wind is going to be either going in the same direction as you, opposite to you, or kitty corner to you. It feels like at West Point, I don't know why, it's always against me. I'm not sure, like, if I walk to Arvin, it seems like it's going against me. If I come back this way, it's also coming against me. I don't know how that's possible, but it seems possible here. But you're either going to get a resistance or some kind of help from the wind. So far, so good? Does everybody understand what I meant by this? Like, I plug in X and Y and I get a vector. And that vector tells me the direction, and the magnitude of the vector tells me the strength, the force of that wind. So again, to see it with numbers, I think I told you guys this. I'm named after St. Thomas, the doubting Thomas. I got to see the beliefs. I got to see some numbers. Here's what the numbers will look like. The kind of data you would need is you need position, again. You need where you are on the curve. You would need the vector that represents at that position the force of that wind and the direction of that wind. So that's what this is. You need the direction the soldier is roughing. You need to know that, otherwise you're not able to figure out if the wind is helping or hurting. And you still need your delta F. So those are my measurements. I have a lot here to how to interpret that data. So like if I have F of 0, 0 equals 2, 0, which way is the wind blowing? That's right. And how strong is it blowing? 2. And that comes from taking the magnitude of this. 2 squared plus 0 squared and then square root. So that's what it tells you. The direction of the soldier's motion being 1, 0, it means the soldier is also walking to the right. So it's a helpful. I wanted to show you what that looks like. I can plot those vectors in 3 space with the curve so you can see it. Only thing new, you have your curve. The only thing new here is you've got now this vector field. Digested? How does your Riemann sum change? If I wanted to do the same calculation, soldier's walking, I just want to know how hard she's worked by heartbeats. So what I'll do, what's accumulated around the path is I have this dot product. Why dot product? Because dot product is the angle between 2 vectors, and it tells you the direction. If the direction's the same, the angle is going to look different than if it was orthogonal, if it was, like you can get that from a dot product. The dot product is a proxy for the angle between those 2 vectors. And so toss that in and sum it up, you have the same Riemann sum. I walk you through a little bit of the Riemann sum stuff here. We're really adding up a factor now that's telling me if the wind is helping and hurting. All right, last piece. If I was scared by the position factor with a C, this really looked weird, but it's just notation. the formal notation for calculating that total heartbeat, that cumulative heartbeat over that curve with wind resisting or helping is this. That's the formula. They have it in your book with physics examples. Like work. Those are a little bit harder to understand, I think. That's why I'm using the same example one. I hope this example makes everything clear. And I do a calculation for you. I'm not going to make you go to boards and do this, but I do want you to jot this down onto your sheets. We still have the parameterized path. That stays the same. We still have the R of t. We still have, what's new is we have this vector field. I have to calculate the derivative of my R of t, like before. That's the direction that the soldier's moving. And I don't have to do arc. It's already, I don't have to do the arc length factor. It's already covered in here. Remember R prime of t was a part of the previous one? I already captured it here by taking the dot product. And so I get this. Yeah. To the previous page. I did the calculation again. I have now a dot product. This dot product is in the remount, and the more you write, it's going to help you. This is to help you to understand what's going on. You have this dot product in here. So I give you an example. If I have the first wind vector and I have the first soldier motion vector and I take the dot product, that's that part. And then the second one looks like this, the third one looks like this, and then you just sum them all up. So your rerun sum looks a little bit like the original one, it just has some more pieces. Any back, you need to back it, it's fine.
No, I still need to see that.
This block is traditionally thought of as the toughest block. I'm going to see if I can change that because I want, if you see the right things, I don't think it's as tough as it appears to be. Yeah, this is the plug into the formulas part. So what I wanted to tell you guys is one of the things for elementary ed in the class that I learned about teaching elementary students is that you can't just show it with the numbers. You also have to show it symbolically. You can't just give them manipulators and say, add this, do this. Like if I have 2 of these and 3 of these, you actually have to put the symbols. So you make the connection. But little people and big people are the same. We have to see it in notation too. Otherwise it looks scary. Some of you are honest. The phi looks scary. Seeing a phi and a theta and a rho and all these Greek letters, it makes it look scary. So seeing it more often, it helps. What's the difference? Taking these things and knowing how they're different from each other, maybe we'll have a running table, but the scalar interval that you started out with is what you do along that path. A vector adds how the field interacts with how some kind of field, like wind, interacts with that motion along the path. So in your book, they'll have stuff with particle motion, the soldier's a particle motion walking along the path.